let us discuss about the, so we have been discussing about the different micro actuation. Now let us discuss about the micro actuation configurations and the overall mechanism which are involved for micro robotic application. So as far as this, in the case of micro robotic applications is concerned, one of the key important micro manipulation is called as a stick slip actuator. So when we take an example of this stick slip actuator, so these stick slip actuators are efficiently used for a kind of a less than 1 micron resolution. It can be used for creating less than 1 micron resolution. So that is one advantage of this stick slip actuator. However, by reducing the overall configuration of the probe appropriately, we can have a control over the motion of this stick slip actuator. So like these stick slip actuators is defined as a precision motion device utilizing the controlled friction phenomenon based on the principle of the inertial sliding or the friction inertia. Also, these are also known as an inertial piezoelectric actuators or piezoelectric inertial diodes. It creates a displacement through a controlled alteration between the static and the dynamic friction, and it offers an advantage towards simple structures, higher resolution and theoretically unlimited strokes. So in this particular case, let us consider this is a kind of an initial portion where there is a stick face is there, and then with the stick face through an inertial force it is slipping to the next level, so that we can have a kind of a displacement which persists over here. Now the generation of this stick face to the slip face is happening because of the piezoelectric actuation which is being deployed over here. So what is happening is, like either the piezoelectric can be incorporated in such a way that at a single stretch you can push the actuator, or in a multi-stage stretches, like when one leg actuates the other leg can come down, or when the other leg actuated the one leg can, that is one feet can come up and the other feet can have a less force exertion and it has a higher force exertion. Through this process also we can have a higher operating process. So as far as historical development perspective point of view, it was first introduced in late 1980s, basically for scanning tunneling microscopy application. So originally the stick slip phenomenon was designed by Niedermann Emsch for a precise positioning, which is evolved for a simple design to sophisticated mechanism with amplification structure. So the major advancement occurred in early 2000s with the introduction of flexural hinge mechanism. So modern design incorporated multi-degree freedom and a bidirectional capabilities has been deployed. When we look into the overall working principle of this stick slip phenomenon, it operates based on a controlled asymmetric motion cycle, as I had discussed earlier. Two distinct phases in each motion cycle can exhibit. One is called as a slow extension phase, where it is called as a stick phase, where a piezo element gradually expands and moving a slider by a static friction. Another one is called as a rapid contraction phase, which is called as a slip phase. So as far as in this slip phase is concerned, a piezo element quickly retracts, a slider maintains a position by an inertia. Now the net result of this is a kind of an incremental forward motion of a slider relative to the starting position. So there is a kind of a repeated cycle which creates a continuous stepping motion. So if you observe over here, so this is the overall configuration of a stick slip and this is the overall configuration of the features. So in this particular case, so we have an increase in voltage and then there is a slip which is observed, and then in the case of a stick phase again there is a kind of increase and then there is a slip is observed in this particular system. So as far as in this, when we closely observe the sawtooth waveform, which is typically used as a driving signal, during a slow ramp of 90% of cycle, piezoelectric elements gradually extends. Static friction between the driving foot and the sliding moves them together, and platform displaces equally in the piezo displacement multiplied by the lever ratio. However, during a rapid return, that is around 10% of the cycle, the piezoelectric element rapidly contracts and inertial keeps slider in a position while driving the foot return. So the dynamic friction is insufficient to pull the slider back. Some of the core components of this particular slip mechanism is concerned. One is called as a piezoelectric stacks, which provides a primary actuation force to the system. So this is the overall figure for stick slip mechanism, where there is a piezoelectric stacks with the stator motor and direction is there. There is a flexural hinge stator is there, a driving foot is there, and a slider change and a base structure is there. So these piezoelectric stacks provides a primary actuation force, a flexure hinge mechanism which converts and amplifies a piezo displacement, a driving foot which is a contact interface with the friction surface, and a slider stage which kind of a moving element that receives the net displacement, and there is a base structure which supports and aligns the component. So these are some of the examples of the type of stick slip actuator. So it's a kind of a linear actuator which achieve high line motions, a rotary actuator which produces a kind of angular displacement. And when we try to classify the same with reference to degrees of freedom, so it's a kind of a single axis system which exhibits, then there is a kind of a multi-axis system which exhibits, and then a kind of a 6 degrees of freedom which persists with a high precision platforms can be established using this particular system. Now, as far as classification perspective point of view, the classification of these kind of stick slip actuators can be either in a unidirectional or in the bidirectional, or it can be on a cooperative mode. So unidirectional means like one way, and the return you may need to manually move it. Bidirection is something like in this particular direction. Cooperative mode is something like this. It's a kind of an adaptive structure. So in this adaptive structure, based on the a kind of an obstacle which is being avoided, so based on the obstacle, so appropriately it can be used for the movement. So with reference to operating characteristics perspective point of view, the stick slip actuators has a direct relationship between the voltage and the displacement. As the velocity increases with the driving frequency, until a mechanical limitation, the performance varies with the preload force which is applied between the driving foot and the slider. As far as coefficient of friction perspective point of view, the coefficient of friction at the contact interface is studied, and the driving wave form parameters, basically the frequency and amplitude are asymmetry to the system. So with reference to application perspective point of view, these kind of stick slip phenomenon, stick slip based actuators are efficiently used in precision positioning system for optics and microscopy. So as termed there, it was used for scanning tunneling microscope. It is effectively used for semiconductor manufacturing of equipments like semiconductor based systems, and then it is also used for medical devices requiring precise motion. In certain cases, it is also used for scientific instrument for nanoscale research. So in the area of metrology as well as in the area of inspection, it is used for a camera focusing mechanism, and it also has an adaptive optics for astronomy and a micromanipulation tool. Some of the key advantages and challenges of this particular systems are: it is a simple structure with few components, and in fact, if you keenly observe the overall construction of this stick slip mechanism, it has only 2 feet, 2 feet as mentioned there. So the appropriate actuation of these 2 feet is highly simple in such a way that it can have a control over the micro positioning level, as well as it can go for a higher order this one. It has a high resolution and position capability. Theoretically, it has an unlimited travel range. It has a low power consumption, and there is no backlash or mechanical play. Challenges perspective point of view, it has a backward motion during a slip phase. A wear at a friction interface. It has a limited load capacity, speed limitation, and environmental sensitivity. So when we try to observe the future research direction of this particular system, so enhancing the speed of it through an optimized fluxural design is one of the need which can be expressed. Second is improving load capacity. So as far as currently these stick slip phenomenon are efficiently used effectively for micro robotic related application. However, for a larger perspective it may have its own impact. Developing a multi-degree of freedom actuator is a challenging task. So of course this stick slip, either as I had mentioned earlier, either it might be a unidirectional or it might be a bidirectional or it might be an adaptive. A multi-degree freedom is one of a challenging tasks. So what we may need to do is, like when there is a leg is there, so by giving there is a kind of a small cushioning kind of arrangement which is there. If this cushioning has an adaptive structure, so appropriately by adjusting the cushioning we can have a rotation. With reference to implementation perspective point of view, like implementing a closed loop control system is one of the important aspect, and exploring an alternative driving waveform beyond the sawtooth. Miniaturization of micro robotic application is one of the challenging tasks by using this stick slip system. In summary, the stick slip piezoelectric actuator provides precision motion through ingenious use of frictional dynamics. A various design approaches offers flexibility for specific application requirements. The performance continues to improve through a research advancement and represent an important class of positioning device bridging a micro and macro scale. Future development are likely to expand application in the case of emerging devices, or the emerging technologies are some of the key aspects. Now let us discuss about the next type of actuation system, which is called as a COM drive based actuator. So as far as this COM drive based actuator, so when we had discussed about this electrostatic process, we have discussed a lot about this COM drive actuator, and now in this particular lecture we will discuss about the overall configuration of this COM drive actuator and its behavior. So with reference to COM drive perspective point of view, it's a kind of a micromechanical system which actuates using an electrostatic forces. The key features of these COM drive actuators includes, it's a simple structure, and it is of easy fabrication, and it is of low power consumption. So it has two basic components. One is a two electrically conductive comb, one is fixed and another one is movable. So this, either this might be fixed and this will move in any domain. Now this is the overall working principle of a COM drive actuator. So in this COM drive actuator we have a fixed electrode in place, and there are anchor points are there, and then there is a mobile structure which exhibits, and these will have a kind of a linear, these are mainly meant for linear actuation. That is, either it can be moved in this direction or it can be moved in this direction. So these electrostatic attraction between the interdigitated comb fingers exhibits, and its applied voltage creates a force drawing a comb together, and the net proportional is applied to the field. Now if we try to see the overall mechanism of this, so we have two fixed combs, and then there is a movable comb. So this is a kind of a fringing field, which passes between this comb. So when we try to look into the parameters of it, like if this is the structure, we have W, G2, G1, sorry. So this is the two fixed combs, and this is a movable comb. So this can be nomenclated as W. W is considered to be the width, T is the thickness, this is G1 and this is G2. So G1 and G2 are the gap between the combs, X is the overlapping length of the combs. So the comb drive actuators has a movable and a stationary structure which split in the fingers with the attached combs, and stationary parts are connected to a ground fixed suspension. So the Coulomb forces deflects the moving comb structure and generate an output displacement, and the comb drive electrostatic actuator can have a lateral and a vertical design which relates to the layout of the comb. The voltage controlled the comb drive actuators are quite attractive in micro positioning because of the lateral exposed electrostatic force independent of the position, contrary to the parallel plates. So the biggest disadvantage of a comb drive actuator are a moderate driving voltage, the small offset in the direct current driving mode, and larger layout area. But however, they can be compensated by a higher displacement rate than other actuators. So a vertical comb actuator is used to have a higher and a greater angular moment, and the design of the vertical actuator with the comb drive brings a higher deflection angle at a low voltage. So with reference to structural and component perspective point of view, so these are the different structures which exhibits. One is called as a fixed comb structure, which we call it as a stator, and then other one is called as a movable comb structure, which is nothing but a rotor, and a flexural spring for suspension and restoring force, and an anchor for a mechanical support, and an electrical connection for the applied voltage. So these are the different structure and components of the motor. Now when we try to talk about the overall comb drive actuator, so in this comb drive actuator, so the amount of force generated, it depends upon the number of fingers, T is the thickness, epsilon is the permittivity of free space, V is the voltage, and D is the gap between the fingers. So with reference to the comb drive operation perspective point of view, as we had discussed earlier, the comb drive operation basically depends upon the gap between the fixed and the gap between the fixed and the movable system, and the overall overlapping length, which is nothing but the x, and then the width of the finger. Now, when we try to look into the key design parameters of this COM drive actuator, the number of some of the key design parameters includes, so the number of comb fingers, the finger dimension, which includes the length, width and the thickness, the gap between the fingers, the overall spring stiffness and the applied voltage are some of the key design parameters. So, as discussed earlier, so based on the number of fingers, based on the thickness, based on the permittivity, based on the voltage and based on the gap, appropriately we can have these parameters will have an influence on the overall electrostatic force which is being generated. However, with reference to performance characteristics perspective point of view, typically it has a displacement range of around 1 to 100 micrometer, and it has an actuation voltage of close to around 1 to 100 volt, and the force generated is in the range of micronanometer to micronewton to millinewton range. So, there are different types of comb drive actuators are there. One is called as a linear actuator, where it is mainly meant for a kind of a linear action. A rotary actuator, so this is a kind of a linear actuator, or it can also be considered as an in-plane actuator, and this is a kind of a rotary actuator. So, in this rotary actuator, so there is an actuator, there is an anchor, and then there is a fluxured ring which is available with the rotary comb drive. So, this rotary comb drive moves in this particular direction along with the anchor. This is a kind of an insert image for it, which gives a clarity like how these systems can be deployed, and like the overall angle theta can be easily represented in this case. So, there is one more kind of actuator is there. So, apart from this, there is a kind of an outplane actuators are also there. Outplane based comb drive actuators are used effectively for different applications. Now, we can also discuss about one of the important type of actuator, which is called as a single sided actuator. So, as far as in the single sided actuator is concerned, so this is a kind of an electrostatic comb drive which is used in a movable micro system with a nonlinear spring. So, like the system looks something like this. This is the movable actuator. With a spring arrangement and a base, and a spring arrangement as a base, Kx and Ky with area A, this is a fixed actuator, and this is a movable. So, this is a kind of a area which is being exerted, and there are two nonlinear springs are there. These nonlinear springs are capable enough in such a way that it can give a kind of a, it is used for a dedicated manipulation. Basically, these kind of systems are effectively used for biomedical related applications, where it is used for dedicated manipulation of tissue samples, and simultaneous with the motion it can measure the displacement, and for probe tipping also. So like it has different geometries and it is being effectively used. Ideally the overall manipulation is taken care by this nonlinear spring. That is, along with the electrostatic comb, a nonlinear spring will also participate in this particular structure. As far as application perspective point of view, like these comb drive actuators are effectively used in optical systems, basically for mirror shutters and switches, RF MEMS system, variable capacitors, and as well as tunable filter applications, and inertial sensors, basically accelerometers, gyroscopes, etc. Biomedical devices including micromanipulators and cell sorters, and it is also used for precision stages, especially in the case of micro robotic systems are concerned. It is used for cell sorting, micro manipulation, and precision stages. Okay, so these are the three applications which basically these kind of comb drive actuators basically focus upon. Now, with reference to advantage perspective point of view, so it has a simple fabrication process. It is compatible with standard MEMS manufacturing. It has a low power consumption, large displacement capability, high force density, and a linear force to voltage relationship. Challenges perspective point of view, it has a pull-in velocity at high voltage. It has a limited force output. It is highly susceptible to stiction, and it has a wear and a wear and fatigue in moving parts, because like it is a kind of a concentrated region. So in these concentrated regions, there are chances are there that it may lead to a kind of wear and tear on these particular parts. Now, with respect to recent advancement and optimization strategies perspective point of view, a novel spring design can be employed for generating a larger displacement, as mentioned in this particular single-sided electroactive system. Asymmetric comb finger design for increased force. It uses an alternative material, example polymer, for flexibility, increasing the number of comb fingers, the reduction in the gap between the fingers, and it has quite a good amount of implementation with respect to the closed loop system. With reference to future direction perspective point of view, this has quite a good amount of integration with other actuation mechanism. Development of a 3D comb drive structure is considered to be one of the key aspects. Application in emerging fields, like in the case of microfluidic related applications and energy harvesting related applications, are some of the focus of these particular comb drive actuation, and miniaturization for NEMS based systems. So overall, in this particular module, we had discussed about in detail about the shape memory alloy structures. We have discussed about the different configuration of shape memory alloy structures, the overall challenges involved and the actuation involved, etc. So we have seen some robotic application, micro robotic applications related to shape memory alloy structures, where we had discussed about a kind of a Stewart platform which is used for fabricating, a micro Stewart platform which is used for manipulating a beam. And then what are the different micro fabrication steps involved in fabricating such kind of shape memory alloy based structures. Then we had a discussion about the conducting polymers, the properties of the conducting polymers, different actuation mechanism involved in the conducting polymers, the key properties, the device architectures, the overall applications, future directions. So we also had a discussion about the shape memory alloy polymer and the electromagnetorheological based fluids. So we had a detailed discussion on the stick-slip phenomenon, how these stick-slip phenomenon are impacted. So it has a potential application towards micro-robotics. What are the different core components which are involved in this stick-slip phenomenon, overall operating characteristics, advantages, challenges, and the future direction. So we also had a discussion about this comb drive actuator. What are the different characteristics of a comb drive actuator, the structural components involved, the basic operation involved, the overall force generation, and key design parameters, as well as the kind of different types of comb drive actuators which are being established with suitable applications, advantages and limitations, and about the perspective of recent advancements and future directions. So these are some of the references which we have used for preparing this particular model.